So, hi everyone, this is Yaorong, and I'm going to be talking about the second order blind identification method based on this review paper. I will I will try to following the step by step from the review paper, but I will try to go through details from the references of that paper because it has more details and intuitions of it. And I will go through the four steps. First, we need to go through about the basic ideas of blind source separation and ICA and some popular algorithm. I won't go through that is because for second order based method is kind of using different theoretical basis to resolve the problem. And for second order, it's more like correlation or covariance something. But for some our familiar method like informatics, based on something like higher order statistics or entropy things, if you for your understanding. And I will go through why the SOBI using this kind of logarithm is based on some kind of joint diagonalization method. And then I will also quickly go through some variant of SOBI logarithm, because SOBI is kind of a very straightforward blind source separation method. It do have some limitations when the data have some specific characters, and people doing some concentrate or advanced ways to optimize these kind of things. And give a quick demo or application from this paper of how these things work. So first, let's summarize the problem. So as you know, if you're ever taken any machine learning class or learn from online of this ICA problem, you may know about the cocktail party problem. It's like in a room, we have a couple of microphones or receivers, and there are a couple of speakers there, which is kind of the sources we're trying to get. Because what we have is only the observations from this microphone or receivers. And because all of the speakers, we consider it as the instantaneous happen thing. So the signals we receive is kind of a mixture of the sources. So which like all of them are speaking together, but we want to separate them. And we consider this precise a linear mixture precise, consider as a transformation of A. And S is the original forces, and what we have observation. The only thing we have is X. So everything we have. And for the transformation, the forces is unknown. So we're trying to find a transformation which can inverse the observation back to what the expected result was as close as to the original forces, and W should be expected to equals to the inverse of the transformation matrix. So this is both BSS and ICA problem trying to solve. And some popular algorithms, Informatics is one of the most robust ICA algorithm, and it's used a lot in neuroscience. And it's also considered the best one for neuroscience works. And it is based on kind of maximizing the mutual information between the input X and the output Y. And by some inference is similar to maximizing the differential entropy of the output. And another way is the fast ICA is and both our Informatics and fast ICA is assume that the sources are independent. What they do is trying to using a transformation to make the separated components as independent as to each other. So this kind of non-Gaussianality and entropy, both things can be evaluated these criteria. And fast ICA using kind of central limit theory, based on the central limit theories, they're trying to make all the components as non-Gaussian as possible. And they were trying to use some higher order statistics like kurtosis and skewness, which is not using in SOBI. And so our main topic for this presentation is SOBI, which is based only on second order, and Jade I listed here because it's also kind of a joint diagonalization method, but it's not using second order. It will kind of diagonalize on the higher order cumulants. So it's to some extent this different way. I will not go through that, but at least you here. So for SOBI, it can be simplified as a very simple formula here. So R is can consider as a covariance or autocovariance functions. It's trying to minimize or diagonalize of some of this of the list of these matrices. I will go through details of what are these things, but basically their objective is just simple as this. So some other statistics still listed here. First one is the mean. The second order variance and higher order skewness kurtosis. We only care about the second one. So for some intuition from our understanding of SOBI, like we know that for the assumption from independent component analysis, they're trying to assume that the forces are independent. But this is kind of a stronger assumption, which some at least second order cannot explain. Even if here's the things, even if we consider two Gaussian distributions are independent to them, but when you have a finite number of samples, like you have 10 or 20 of the samples from two Gaussians, they can be highly correlated. It is possible happens. So sometimes independence is not very powerful to separating things. And what SOBI assume that is assume that the signals are uncorrelated and also they have a kind of unique temporal structure of forces. This kind of assumption is really powerful when you're separating signal-like data. It's not when you can have some spatial correlated data, it will fail a lot. So uncorrelated thing, people should know that it's just like the uncorrelated covariance or disappear, some correlation is 0, and they do not have a linear relation in space. But what is temporal structure is kind of there will be a time lapse. Let's consider this signal here as what we call an autocorrelation is like if we define the time lapse as let's say 200 here. So the autocovariance here will be the first part of signal is 0 to 800 and another intervals from 200 to 1000 and then compute the covariance between them. This is what we call the autocovariance in this paper. And this is and this covariance matrix is considered as diagonal. So this is an assumption based on SOBI mainly. And also based on this, you can that's next. And so what are these things can be helpful? It's because if we consider the covariance and their autocovariance are diagonal, which means that we need to find the transformation that makes the transform the mixture, transform the components as uncorrelated as possible in different time intervals. So the tau represent the time intervals, like tau equal to 0 means a covariance matrix. So R0 is just yes, in general, like the BSS problem will have some noises there, and autocovariance method can, to some extent, avoid the error of the noises. Let's see how it does. So for covariance, the autocovariance will be like the R as 0 represent the covariance. A is a transfer matrix, so the covariance of our observed signals will be represented with sigma square represent the variance of noises through each dimensions. And by compute autocovariance, because remember what we talked about the interval things. For the autocovariance of the noises, because this is not assumption. Assume that the noises are white noises. So the autocorrelation of the noises in this condition will be 0. So by compute autocovariance, the noise part can be neglected. So if you can find some kind of transformation that can diagonalize each of the covariance and or autocorrelation matrices, it's a direction to find the final mixing matrix. Is it clear here?
What does the H mean next to the H?
Oh, H is transpose because it's based on like things based on the complex number.
Oh, okay.
So it's transpose. And as we know, winding is very necessary for IC problems. Will significantly improve the performance of IC logarithm. And people don't know why using winding, but here in SOBI, it's have a very meaningful work because their joint diagonalization is based on trying to find some orthogonal matrix. I'll talk it later, but let's see what the winding do in the SOBI works. So winding is achieved in PC. I will not go through details of how the PC getting the winding matrix and the W is a winding matrix. So the covariance of the whitened matrix can be computed like that. W times YT is a whitened matrix and times its transpose is expectation is the covariance of it. And RY0 is represent the covariance of our observed data. And observed data is a transpose of the original forces. And based on the assumptions, the covariance of the original forces is diagonal. So which means there should be is identity or diagonal. After one is identity. There should be identity here, just remove it. And so by the inference can say that because the widening correlation will be identity, which means that WA times A transpose W transpose will be identity, which means WA is unitary matrix or orthogonal matrix. Unitary matrix is still kind of complex definition there. So in this condition, we will see that WX to U, which is a orthogonal matrix, because A is the matrix that we're trying to get. So we can represent A equals to W transpose times U. And the problem of finding finding a W or inverse is trying to find a orthogonal matrix that can rotate the W transpose back to the mixing matrix A. How this can be achieved. So then there's coming from the joint diagonalization. So what is joint diagonalization trying to do? Is like when you have a set of M matrix, let's say is positive defined generally. People are trying to find a orthogonal matrix V that can rotate the matrix M1 to K at the same time to make them as diagonal as possible. So basically this kind of logarithm is trying to find this kind of orthogonal matrix based on our work based on the previous things. We're trying to find this kind of orthogonal the orthogonal matrix U here. And so this is how the autocovariance is coming out. Because you simply diagonal the covariance matrix of like tau is 0. This is just covariance. It's just doing the widening work. But when you're adding tau here, which means you're adding covariance, and you have a list of these different taus. And for selecting tau is always a trick until now, and I will talk that later. And so people so we have this list of M matrix from covariance and to different time legs autocovariance. We have a list of them and run the joint diagonalization algorithms and to find the orthogonal matrix V. And it's trying to minimize this work. This is what I mentioned before, is trying to have that objective function. And for joint diagonalization, is a big talk. I feel like it's it's a large topic and there are a lot of algorithms trying to optimize this work. I will not go through that details of how this algorithm works. They will use kind of some different ways, like becomes there's more of linear algebra, and I'm still not fully understanding, but the idea is trying to minimize off diagonals of all the autocovariance matrices. And if you're interested in this algorithm, at least one of these here, this is the latest one I found, which is and very powerful to join diagonalize of all of this paper, all of these matrices. And but one thing I want to mention is of the uniqueness of joint diagonalization. So here, let's go here slowly, because like here's the theorem that the uniqueness is be confirmed with when among all of this matrices there exist two let's start again. We have a list of these M matrices and we're trying to find the U that to have a diagonal, there will be a diagonal matrix that can transfer back to the M matrices. And which the U is our definition. If it's based on the assumption of the diagonal thing, the D will be a diagonal only matrices. And it's more like an eigenvalues there. So for here, the joint diagonalizer of M is essentially equal to U. So which means that for any components for any two eigenvalue in any two eigenvalues in one matrix, there should exist one from this K matrices that the eigenvalues are differences. I don't know if it's clear, but maybe it's reading that is more clear. But how to prove that? So all of these theorems trying to make it sufficient that to establish by proving that there is at least more than two rows from the U, and their linear combination cannot be an eigenvector, a common eigenvector, which is an eigenvector for all of the K matrices. And how to prove that is they assume there exists a linear combination of all of the rows of the unitary matrices, and which is V. If we consider it as a common eigenvector of this, which you will have this because V is a common eigenvector. So which for no matter which the matrix is from the M, it's equal to lambda K is the eigenvalue times the eigenvalue of that matrix is times the eigenvector. It's just an eigendecomposition. And because V can be represented as a linear combination of this, so it can also be represented as the summation of this part. And also for this part, V can also be represented as AJ times UG. So it's based on the summation, and it will also equal to the common eigenvector times the eigenvalues here. So which based on this identity, what I mean is this part and this part should be equal if there exists a common eigenvector. What they're trying to do is that there is no eigenvector, but if it exists, there will cause a problem because in this condition, the AJ times this part, because there is only difference lambda K and the one of the eigenvalue and the J eigenvalue. So there should be one of this part, either IG or the one in the bracket should be zeros. And so things they assume that A1 not equals to 0. And because they said at least two non-zero factors here, and because A1 is not equal to 0, which will cause the lambda K will equal to D1K, because A1 is not 0 here. So which means the DGK and lambda K will be 0, which means they are the same. So in this condition, it will cost the ice linear mixture will be 0, and which will offset the assumption here. So, and also, okay, so the next paragraph states the things I will not bother that because this one will opposite the cannot more than the common eigenvector things. There to some instance prove that uniqueness of joint diagonalization. I think it's more better if you can write it down to visualize how this really works, be more visible. And so at least prove that the joint diagonalization process will lead you to a unique result, which you're looking for a solid matrix. And so steps of solving is it's just straightforward what we have explained. The first and second steps is just writing precise. And then you're trying to, then you list a list of matrices with different 10 legs and do joint diagonalization among these matrices and you will get the results. At least I was planning to put this part before our explanation, but it seems like because I'm trying to say the SOBI is kind of advanced version of the second one. It's used as a logarithm for multi-unknown signals instructions. It's kind of based on just two matrices, trying to join diagonalize between two mutual covariance and one autocovariance matrices. And they found that based on, they give all this idea of the unique autocovariance things and trying to make them diagonal. And then people then in 1997 and trying to make it, if we have this unique feature, why don't we use a couple of them? It will make it more robust. And they invented a logarithm to do the joint diagonalization, and people trying to update until now. Some other JD method invented. And I put this one here is because this one's I found from a book considered as the earliest paper using joint diagonalization. It's not popular, but people trying to, at least people starting to doing that. Some limit.
Quick question. Which of these papers has the proof? The uniqueness proof?
This one. It's the last one. Some limitations of SOBI. As I mentioned before, the time legs is one of the crucial things because from my experiment from SOBI logarithm, some of them will use like 1,000 of this kind of matrices when the signals become very, very long. And some of the legs may not capture the temporary feature, and it will give some compensate on the final result. So selecting 10 legs are a very important part. And joint diagonalization performance. So generally we cannot fully diagonal all the matrices because theoretically they cannot be diagonals at the same time to some instance because they are not all diagonal at the same instance. So the performance is a really problem. And when you're trying to join diagonalization on a lot of these kind of matrices, it's still like a computation efficiency works. And also it was missed about the method are not good at some of the clustered signals, which they have a large clustering signals, sometimes it will fail. And also the mixing procedures may not stay constant all the time, which means sometimes people using a tensor leveled multiplication and multi-dimensional sources signals like most straightforward example is on FMI, or for simple list, they can consider mixing some images. It can be multi-dimensional. What we see that we can just flatten it as a signals, but it will miss off the spatial features of the images and the robustness. And this is the only one that's that I found mentioned about trying to say the outperform the SOBI to some instance, but that's still based on the SOBI method. So here's I would just quick list up because all of them are still very similar based on joint diagonalization. They just trying to find some tricks to find time lags or using some other transformations on their covariance matrices. Like this is trying to solving the clustered problem, but actually I don't have access for this paper. I didn't go through the details, but from the reviews they say that they did not mention if the performance really improved or not, but they're trying to make like a continuous differentiable function to do the transformation of this u times x st is the whitened signals. And also based on multi-dimensional SOBI, it's everything still the same. Same calculate covariance, same computing of autocovariance, just everything is based on a tensor level the multiplication. And here's a result from the paper. I list here is not want to say how they performed on the fMRI data. I want to mention something else. Well, there's some information about the data. And what they're trying to do is like they're doing a tensor level multiplication is based on this precise. But I want to mention this is because as I know, I see what fMRI is trying to get the blobs of each of the regions when you're doing some task or even rest. But this one seems like has a relative bad performance. I want to mention that it's not about on fMRI, more want to state the SOBI on images level, because it cannot capture the features on the spatial one. Like if you do this work, it's kind of, you may stretch it, flatten it to a vector. And when you, like if you pick this part, these intervals, and the autocorrelation will be based on everything, all of the other parts of the brain, even if it's a mask. But what we care about is only this two parts, just two small, tiny intervals. I'm meaning two distinct rows. So they will have more like relations and trying to be extracted. So we cannot perform well. And I also did some experiments based on my stimulated mixing on images. So we can later feel, but it's performed really well on separating speaker or speeches. And another one is the robusto. This one also they instate that it's kind of outperformed the SOBI, but it's not a well known or well studied paper because it's not about the same SOBI. The intuition is from it. They're trying to standardize the covariance precise. And what people invented called the ESAM SOBI, which is they instead that outperformed it. But what they're trying to do is they kind of change some like the criteria, the term mu and the covariance by represent of this. I wasn't go through about that. Still, I don't have access to this paper. I will look at it later, but if people who are interested, you may go through about how to use this one. It's the thing that outperforms SOBI. I don't know not to what extent. And okay, then this is some application of their work. They're trying to say how performance of SOBI on the ECG data. And the left one is from the ECG from a pregnant woman, which is trying to detect the heartbeat of the baby and woman, and using like 8 sensors to do that. And there is a combination of SOBI and the the general survey. What the general survey doing is they trying to found what they call the better legs for doing this kind of works. But I do not see much differences here, and also for the paper, they do not mention about the efficiency of which one is better. It's just listed some of the results here, but still for 10 legs, because this work is based on just 12 10 legs. If there's going to a longer 10 legs, the result may be, I guess, will be significant difference. Okay, I think that's all.
That timeline in this one, is it bigger than the period of ECG?
What?
Is it bigger than one period of ECG? What is the resolution?
Oh, okay, I think it's screenshot. So the timeline thing is just from 1 to 12.
12,
Yes,
what
1
is the
to
sample rate?
What?
What is, do you know what is the sample rate? I'm asking if the lag is equal or bigger than the period, so that's fine, right? If you include high time lag, you just repeat the information, it's just a. Because ECG is quite periodic.
It's just 12. It's just using 12 10 legs and the total loss 1200 to 500.
Okay.
So this is what I mean with the use of longer interval. I don't know, because this it's just attached one applications here.
You said you use it for fMRI too, right?
I tested.
What is the time lag you use?
I found some online called this to trying like 1,000.
1,000?
Yes, 1,000 matrix. But I feel because it's not like a multi-dimension, it's just I just flatten it, consider it as a signal. So it's failed for sure because the spatial structures cannot be captured by just autocorrelation form.
You can actually do that, just have to do it right. There is a way to do that.
Yeah, there should be, but I
It's not
have
just flat.
yeah, yes. I was thinking of like going through like a specific direction of the dimensions, and that is their way computer covariance. The trick is trying to capture the the changing direction, but it's more like feels like it's more like continuous changing. If there's a jump, then it's gonna fail. This when you flatten images, the relation is more like if flatten my face, so this part and this part will be all of this. And, that's for it's more like just trying to deliver everything. It's not from ChatGPT. Any comments, questions?
So what's the takeaway?
What?
What's the takeaway? You've read it.
It's not good.
Yeah, because what are the benefits of survey compared to the other lines of separation?
Oh, it's very strong on signals. It's very powerful on separating signals. I tested, it's stop recording.
It can only be used on 10 series data, right? It doesn't work on spatial.